Hey everyone, and welcome back. In our last couple of lessons, we introduced the definition of a line integral for vector fields, and we checked out some examples. So far though, the only way we know how to evaluate these line integrals is using that bulky definition. We have to first come up with a parameterization for our curve C, then plug that into our vector field, take the dot product with the derivative of our parameterization, and then integrate. Oh, it's a bit of a process, isn't it? Well, today you're in for a treat, because I'm going to show you an amazing new result called the fundamental theorem for line integrals that will make computing certain types of line integrals much, much easier. The statement is as follows. Here we're starting with a vector field capital F that can be written as the gradient field of some scalar field little f. We actually had a special term for such vector fields. We called them conservative. So if we're dealing with a conservative vector field that's continuous along C, meaning that its component functions P and Q are nice and continuous, then the line integral of our vector field along C is simply little f at the end point, R of B, minus little f at the starting point, R of A. Now folks, this theorem is a work of art. It says that if we can write our vector field in this form, then evaluating this complicated line integral amounts to simply plugging in the endpoint and the starting point to our function little f and taking the difference. It's incredibly simple. This is one of the 4 fundamental theorems of vector calculus, and the remaining 3 we'll touch on at the end of this unit. Before we jump into some examples, there's an important connection that has to be made. Hopefully this theorem reminds you of another fundamental theorem, the fundamental theorem of calculus. This result says that if you have a function capital F whose derivative little f is continuous on AB, then the integral of little f from A to B is equal to capital F at B minus capital F at A. We plug in the endpoints to the antiderivative and take the difference. Well, that's exactly what's going on here. Remember, way back when, I told you that you could think of this gradient vector sort of like a derivative, which means little f is sort of like an antiderivative. We're plugging in the endpoints to the antiderivative and taking the difference. Beautiful, isn't it? Now you might be thinking, oh, Zach, the proof of such a beautiful result must be so complicated, right? No, not really. We actually have all the tools at our disposal to give a short proof right here, right now. So let's give it a try. Let's assume that our vector field f is conservative. It can be written as the gradient of some little f, and so it has entries partial f by partial x, partial f by partial y. We're also going to assume that our curve C has been nicely parameterized by some function r of t with t between a and b. We now have to ask ourselves, what happens when we try to compute this line integral? Well, all we have to work with is the definition. According to the definition, this line integral is the integral from a to b of f of r of t dot r prime t dt. That's all we have at our disposal. So we have to do the only thing we can do. We have to replace this capital F with this gradient vector, right? That's what we've assumed. We have the integral from a to b. We're going to replace our gradient vector here, partial f by partial x, partial f by partial y, and we might as well also replace this r prime t with the derivative of this expression here. So I have dx by dt, dy by dt, dt. Okay, we could expand the dot product. That would give us the integral from a to b of partial f by partial x dx by dt plus partial f by partial y dy by dt. Now, does this big, ugly expression remind you of anything? Hopefully it does. This is exactly the expression that appears in the chain rule for paths. This is the expression that you would get from the tree diagram with f at the top, x and y in the middle, and t at the bottom. So we can recombine this whole thing into just df by dt. This gives us the integral from a to b of df by dt dt. From here, we can wrap up the proof with the fundamental theorem of calculus. If we're taking the integral of this expression, then we can evaluate it by plugging in a and b to an antiderivative. Well, an antiderivative for this is just little f. we get little f at t equals b, which is going to be r of b, minus little f at t equals a, which is r of a. And there you go, the fundamental theorem for line integrals. Okay, example time. Here's a quick example that shows off the real power of the fundamental theorem. Suppose that I have a scalar field, little f at xy equal to 2x plus cos xy. I want to evaluate the line integral of its gradient field, nabla f, over certain paths c. First, c is going to be the arc of the unit circle traversed clockwise from 1, 0 to 0, 1. So here's 1, 0, here's 0, 1, here's our unit circle, and we're supposed to be going clockwise. So we're going along this path right here. Now I could look for a parametrization. I could use the definition of a line integral, but why bother? The fundamental theorem says that since this vector field is conservative, right, it's the gradient of some little f, then we can evaluate the line integral by simply plugging in the final point to f, plugging in the initial point to f, and taking the difference. Much, much faster. By the fundamental theorem, this line integral over c of gradient of f dot dr is f of 0, 1 minus f of 1, 0. And I'll let you verify with a very simple calculation that this gives an answer of minus 2. No parametrization required, no derivatives required, very, very straightforward. Okay, what if we change the path? What if we instead take the straight line segment from 1, 0 to 0, 1? Well, again, the fundamental theorem says plug in the final point, plug in the initial point, and take the difference. By the fundamental theorem, this line integral is f of 0, 1 minus f of 1, 0, which again is minus 2. We've done the exact same calculation. To see just how far you can push this, consider this crazy path. The path C going from 1, 0 all the way to 0, 1. This thing looks horrible. I don't know how to parametrize this, but we don't need to. By the fundamental theorem, once again, our line integral is f of 1, 0 minus f of 0, 1. Again, it's minus 2. Now, if in the last example I had given you one more path from 1, 0 to 0, 1, I bet you would have immediately known the value of the line integral. Minus 2. This is all thanks to the fundamental theorem. The fundamental theorem tells us that the only points that matter when calculating the line integral of a conservative vector field are the starting point and the ending point. We don't care at all about what our path does in between. This, folks, is a major consequence of the fundamental theorem. It says that if we are dealing with a conservative vector field, then that vector field is what we call path independent. Here's the formal definition. A vector field is said to be path independent if, whenever you have two paths that start at the same place and end at the same place, then the line integrals along those paths have the same value. I have a quick remark to wrap up this video. We've seen some pretty amazing content in this lesson, but it's important not to get carried away. In particular, remember that not all vector fields are path independent, and we've actually already seen an example. In our last lesson, we explored the vector field f of xy equals x minus y x. We computed the line integral of this vector field from 1, 0 to minus 1, 0 along two different paths. C1, which was the upper half of the unit circle, and C2, which was a straight line segment. We found that our first line integral gave a value of pi, while the second line integral gave a value of 0. This actually tells us some interesting information. We have to conclude that our vector field f is not path independent. We have two paths from 1, 0 to minus 1, 0 with different values for their line integrals. But if f is not path independent, then it's also not conservative. On the last slide, we saw all conservative vector fields are path independent. So therefore, capital F is not the gradient field of some function little f. Pretty neat, huh?